data center applications. Let us start with the motivation behind our work. While preparing for today's presentation, we searched for ISCA 2022 on Google. This Google search for ISCA 2022 took around 520 milliseconds. This latency is pretty good in terms of user experience. However, to serve that single search query, Google had to use 8 processor cores during those milliseconds. Now consider serving billions of users all over the planet. Serving so many users means companies like Google and Facebook deploy millions of processor cores on their data centers. Deploying so many processors over tens of data centers incur millions of dollars in management and energy cost. Moreover, these many processors are responsible for the planet scale carbon footprint and global warming. Therefore, if we can improve the performance for each of these services, even by a few percentage points, we can not only save millions of dollars, but also build a better future for our next generation. To do that, let us see why a single web service requires so much compute effort and where CPU pipeline slots are spent. For an example, when researchers at Google investigated where CPU pipeline slots were spent for Google web search, they found out that only 32% of all CPU pipeline slots were doing useful work retiring instructions. All the other slots could not retire any instructions because of issues in the processor front-end and back-end. In particular, almost 25% of all pipeline slots were lost due to front-end stalls when processor is unable to fetch instructions efficiently. In this work, we first characterize the reasons behind this significant performance bottleneck. In particular, we find that the state-of-the-art decoupled front-end, which is actually implemented in recent processors to eliminate this front-end stall problem, still falls significantly short from the optimal behavior because of making poor replacement decisions in a key front-end structure, branch target buffer, or BTB. BTB caches the target address for taken branches, and data center applications suffer from many BTB misses. We also find that even the state-of-the-art replacement policies fail to overcome these poor BTB replacement decisions, as data center applications have a large number of unique branch instructions. To overcome these poor BTB replacement decisions, in this work, we propose Thermometer, our profile-guided BTB replacement solution. Thermometer collects the execution profile of data center applications in production and analyzes them offline to identify how to make good replacement decisions. Based on this analysis results, Thermometer inject hints in the application binary. And to leverage these hints online, Thermometer modifies the hardware replacement policy so that Thermometer can make close to optimal BTB replacement decisions. We evaluate Thermometer using 13 real-world widely used applications to show that Thermometer reduces 21% of all BTB misses. Thanks to the significant number of BTB miss reduction, Thermometer achieves an average instructions per cycle or IPC speedup of 9%, which is 83% of the speedup provided by the theoretically optimal BTB replacement policy. As an outline for the rest of this talk, first we will show characterizations to identify why do existing techniques fall short. Based on characterizations insight, next we will describe Thermometer's design, and finally we will show several evaluation results to validate Thermometer's effectiveness. Let me start with the characterization. Recent processors attempts to eliminate front-end stall problem by enabling decoupled front-end and phase-directed instruction prefetching. Instead of traditional front-end, where branch prediction unit provides a single phase target to the instruction fetch engine, decoupled front-end introduces a queue between branch prediction unit and instruction fetch engine. Thanks to this queue of fetch targets, when the instruction fetch engine is bringing in the current instruction, the next or future instructions and their corresponding TLB entries can be prefetched using instruction and ITLB prefetchers. To understand whether this state-of-the-art mechanism eliminates all front-end stalls, in our paper, we performed several limit studies. In this specific limit study, for the applications shown in the x-axis, we use a theoretically optimal BTB replacement policy with FDIP and decoupled front-end. This theoretically optimal, yet practically practically impossible to implement optimal replacement policy, always evicts or replaces the BTB entry that will be accessed farthest into the future. we measure what percentage of instructions per cycle or IPC speed up this optimal replacement policy provides on top of this baseline decoupled front end with LRU or least recently used BTB replacement policy. We show this speed up in the y-axis where higher is better. As we show, these data center applications achieve an average IPC speed of 10% with the optimal BTB replacement policy. In comparison, state-of-the-art BTB replacement policies, even the best performing best state-of-the-art provides only an average IPC speed of only 2%. This result suggests that for data center applications, state-of-the-art mechanism falls significantly short because of making poor BTB replacement decisions. Now let us see why do these prior techniques fall short. State-of-the-art replacement policies view the replacement problem as a classification problem. A simple example is to categorize all branches into two categories: BTB friendly branches, which usually result in BTB hits if stored in the BTB, and BTB unfriendly branches, which usually does not result in BTB hits even if stored in the BTB. Consequently, the state-of-the-art replacement policies prioritize these BTB friendly branches to keep in the BTB while sacrificing or evicting the BTB unfriendly branches. Since these state-of-the-art BTB replacement policies are purely hardware techniques, they must learn and store this information purely in hardware. For an example, this specific table shows branch information, whether they are unfriendly or unfriendly for several branches, and these replacement policies must rely on this friendly and unfriendly information to make BTB replacement decisions. However, if one of these branch gets evicted from this BTB and gets executed again sometime later, these replacement policies don't know whether this branch is friendly or unfriendly. In the context of data center applications, this happens a lot as they have many branches, which results in many BTB entry evictions. That is why the state-of-the-art replacement policies fall significantly short from the optimal behavior, as they cannot retain this BTB friendly or unfriendly information for branches after their eviction. Now that we know what is the reasons behind their bottleneck, now let us see among these many unique branches, which branches are worth retaining in BTB. To identify that, we use optimal replacement policy. For all unique branches for data center applications, using this optimal replacement policy, we first count how many hits they result in this optimal replacement policy. We also count how many times each of these branches are actually taken during program execution. By computing the ratio among these two counts, we measure hit to taken ratio or hit to taken percentage, and we compute this ratio for all branches. Now, for all branches, we show these branches in the x-axis based on their after sorting them based on their hit to taken ratio. So 0% of the branch on the left has the highest hit to taken ratio, and branch on the right has the lowest hit to taken ratio. In the y-axis, we show their corresponding hit to taken ratio where higher is better. As we show, a significant number, almost more than 50% of all branches have a hit to taken ratio almost 100%. We call these branches hot branches. On the other end of the spectrum, there are some other branches which has almost close to 0% hit to taken ratio, which we identify as cold branches. In between, there are some other branches which has their hit to taken ratio rapidly declining, which we identify as warm branches. We call this metric branch temperature, using which we can identify which branches are consistently retained by the theoretically optimal BTB replacement policy. Now that we know which branches are worth retaining into the BTB, let us see which branches are worth even inserting into BTB. To do that, again, for these 13 data center applications, we measure how many times each branches of different temperature, hot, warm, and cold branches, are actually inserted into BTB by the optimal replacement policy. We show this percentage in the y-axis where higher is better. As we show, hot branches are almost always inserted by the optimal replacement policy. Similarly, even optimal replacement policy even inserts warm branches most often. However, in terms of cold branches, they are rarely inserted, as even optimal replacement policy does not insert more than 50% of cold branches for data center applications. Using these characterizations from these data center applications, now Shixin will present the design for our technique thermometer.
Thanks, Tanvir. In general, thermometer consists of 4 steps: online profile collection, offline replacement analysis, offline hint injection, as well as the hardware BTP replacement policy modification online. Now, let's take a look at these 4 steps one by one. First, thermometer collects the trace of all dynamically executed branches using efficient hardware methods such as Intel processor trace. This trace contains the branch direction, in other words, whether a branch is taken or not taken, as well as the branch target for each taken branch. Next, offline, thermometer simulates this branch execution trace using the optimal replacement policy. The simulation time is only tens to hundreds of seconds, which is similar to all the profile-guided optimization techniques widely deployed by Google and Facebook. During the simulation, thermometer counts how many times each unique branch has been taken and how many times each taken branches can be found in the branch target buffer under the optimal replacement policy. Then, by calculating the ratio of the 2 counts, thermometer can get the hit to taken percentage of all unique taken branches. Then, thermometer using the hit to taken percentage to classify all branches into different temperature categories. According to our sensitivity study, thermometer performs best when classifies all branches into 3 categories and encode these categories with 2 ISA hint bits. Similarly, using empirical study, thermometer decides to use the temperature threshold 80% and 50%. Then the branches can be classified into hot, warm, and cold categories as shown in this chart and in this table. In x86 and ARM, we know that there are at least 2 bits reserved for each unique branch. Therefore, thermometer can replace these unused bits with the temperature category hints to insert these hints without introduce any overhead to the binary size and use these hints at runtime. Finally, by using these hints and modifying the BTP replacement policy, thermometer is able to make near optimal decisions. Let's take a look at this example. For this BTP set, thermometer is deciding whether to insert this new branch into the BTP set. If new branch is colder than all other branches already in the BTP, thermometer will not insert this branch into the BTP set. For a different example, if the branch is not colder or warmer than any other branches already in the BTP, thermometer will first find out all the branches in the coldest category and then evaluate the least recently used one in the coldest category, as shown in this chart. As we can see that thermometer requires 2 additional bits for each BTP entry to store the temperature information at runtime. This will introduce 2.6% overhead to the BTP size. According to our experimental evaluation, this overhead will only introduce little impact on the performance of thermometer. Now that we have demonstrated the design of thermometer, we're going to show that the thermometer's experimental evaluation. We evaluate thermometer based on several key metrics, and today we'll only show 2 of them. First, we measure the instruction per cycle speedup provided by thermometer. Second, we measure the percentage of BTP misses reduced by thermometer. For both experiments, we will compare thermometer with the theoretically optimal replacement policy. We will also compare thermometer with the state-of-the-art replacement policies such as S3, JHRP, and Hawkeye. For all experiments, we will use different application inputs to doing the profiling and the testing. First, we measure the IPC speedup provided by thermometer over the LRU baseline. The y-axis refers to the speedup, so the larger the better. While the existing works only provides no more than 2% speedup on average, thermometer is able to provide 9% speedup. Compared with the optimal replacement policy, which provides 10% speedup, thermometer is able to achieve 84% of the speedup provided by the optimal replacement policy. Next, we measure the BTP miss reduction provided by thermometer. The y-axis shows the reduction over the aerial baseline, so the larger the better. Well, the existing prior works only provides no more than 7% BTP miss reduction. Thermometer is able to reduce 21% BTP misses. Compared with the optimal replacement policy, which reduces 34% BTP misses, thermometer is able to achieve 63% of BTP miss reduction provided by the optimal replacement policy. In summary, we show that BTB replacement has significant impact on the data center application's performance, since it can reduce on average 10%, can provide on average 10% speed up. We also show that the prior replace policies fall significantly short of the optimal replace policy, since they lack the proper understanding of branch behavior in the data center applications. In this work, we thoroughly analyzed the branch behavior in data center applications to redesign the BTB replacement policy. Based on our analysis, we proposed Thermometer, a novel profile-guided BTB replacement policy. Using the profile collected from the data center applications, Thermometer first carry out replacement analysis to generate useful replacement hints. Then, Thermometer inject these hints to the binary to generate some new binaries. Finally, Thermometer modified the online BTB hardware replace policies to make near optimal decisions with these replacement hints. We evaluate Thermometer using 13 widely used data center applications and show that on average, Thermometer is able to provide 9% speed up. This can save billions of dollars in the real life. That's all for our presentation, and thank you for listening. If you're interested in our paper, please scan this QR code to get the full paper or reach us to via email. Thank you, and we're happy to get any questions.
Hi, I'm Sriraman from NVIDIA. I didn't see anything about your simulation methodology or what is your baseline BTB architecture, but I'm assuming all of that is in the paper.
In the paper.
But a very specific question there. I think your fundamental assumption is that if a branch is not taken, it's not worth keeping in the BTB. That's right? But one of the fundamental issues you see in a lot of front-end pipelines, especially x86, is even not taken conditional branches need to be identified as a branch, because then that's how they update their conditional branch tables. So that's the question, basically. How do you address those branches which, they're going to be not taken, but still it's critical to update your global history for those branches. And you can't do that after decode. You have to do that before decode.
Yeah, that's a really good question. So I think last year's ARM, there is a paper from ARM last year, and there was a IEEE Cal paper, and there was they had another paper, which was the, I think, ISPAS or ISW, I think ISPAS, yeah, ISPAS based paper. They own the best ISPAS based paper. Again, like full, just for just for disclosure, I also collaborate with them as well. So their paper actually showed that you actually don't need those branches in the taken history, global history register. And they actually showed that without including those global history, without including those branches into the global history registers, you actually get better performance. This ISPAS best paper award from last year's paper, you can show that. They showed that.
But your fundamental assumption is that
yes,
that works out.
Yes.
Okay.
That's why we use that baseline, since that's also an industry baseline as well.
Hi, Siddharth Gupta from EPFL. Thank you for your talk. My question is, if we can already profile the branches and analyze the temperature, what else would it take to cover the rest 40% compared to the optimal replacement policy?
Yeah, that's actually a really good question. So one thing that would be really interesting to see is that, like, we identified that these are the hot branches, but there are some cases hot branches stay hot for a long time, but after that time it is no longer hot. It becomes from cold or hot, it becomes either cold or warm or mostly cold. So that transition, you will have to somehow identify those transitions. So to do that, there could be several approaches. It could be something like dead block predictor. It could be some other, like a profile guided mechanism. For example, last year's report, again, like for disclosure, that's also my work. So those kind of dead block predictor or like identifying when the transition happened could help us reach to that other 40%.
Or you could, when this transition happens, you can also place more hints, more complicated hints saying that the transition has happened.
In this work, one of the feedback that we got from our earlier work was that, can we build systems that won't use any extra bit that already does exist on the ISA? So that's why we try to come up with a solution where we only use 2 bits, which are already unused in the Intel and ARM architecture. So that's why we did not go one step further, because even with this just 2 hints, as you can see, almost 60 to 80% of the benefit of all of this application we can achieve.
Thanks.
Hello, this is Feng Jia from Purdue University. It's a good talk. May I ask you, what is the hardware implementation of the BTB replacement policy? I am primarily interested in how you are able to find the coldest branch in the BTB to replace.
Yeah, again, in the paper, we actually mentioned that so most of the time, our baseline is 4-way BTB, like or each set that have like only 4 branch entries for each set. So we actually have a hardware implementation in the paper to actually determine that how can you compare against for all 4 branches, and how can you even pipeline them as well, so that you can actually identify the coldest branch within just 2 or 3 CPU cycles.
Right, thank you.
Great talk, both of you. Just one question from me. So did you try different data sets and different input parameters for these applications, and what was your coverage?
No. Input. Just input. So just like you mentioned, we actually, as all the results that we showed so far today, profile was collected using one application input and evaluation was done on a different input. However, at the same time, we also try to see that we have collected this profile from one input. How does it actually generalize across many inputs? So in this experiment, that's exactly what we did. So we have very many inputs for an application and identify that how much this different inputs profile provides, how much the same inputs profile provides. As you can see this from figure, with a different inputs profile, we get almost 50% of the performance that optimal replacement policy provides. However, with input from the same input, we get up to like 55% as well, across at least 3 inputs for all applications. So yes, it's right. There are some profile representativeness as well as profile dependency, but in practice, as you can see, it does not matter that much. It only like 5 to 10% across different inputs.
Awesome. Thank you so much. And that's a great way to prepare for session questions. All right, we'll move on to the next talk. All right, the next talk is Lukewarm, Serverless Functions, Characterization and Optimization. David Schall, a PhD student from the University of Edinburgh, will be giving this talk, and he is working on investigating the implications of modern cloud workloads on today's microarchitecture. So take it away, David.
Okay, does it work? Okay, perfect. Hello, my name is David, and today I want to present our recent work we did on, just a moment, we did on characterizing and optimizing lukewarm serverless functions. And no worries if you don't know what lukewarm or what serverless means, that's why I'm here for. This work was done together with my colleagues, Artemi, Dimitri, and also with Boris Grot, my supervisor, and Andreas Sandberg, our collaborator from ARM. Let's start by briefly overviewing how complex services are deployed in the cloud. Traditionally, monolithic applications as well as microservices run in beefy virtual machine images that typically stay up for a long period of time. Whenever the service is idle, the cloud customer must still pay for all enabled virtual machines. Entering serverless, which has a radical different cloud execution model in which applications are decomposed into a collection of stateless functions that run only on demand. When there's no demand, so no invocations, nothing runs and the cloud customer doesn't pay. Cloud customers love that, and no surprisingly, the adoption of serverless has been skyrocketing. In the serverless programming model, developers implement their application as a collection of stateless functions. The functions are invoked on demand via trigger events, and the functions are statelets, which is nice because it facilitates on-demand scaling, scaling down to zero. Developers only pay for the time the CPU is actively processing the function, and also only for the memory the function is consuming. And so developers have now a financial incentive to make the function short and small. And because of the small memory footprint, cloud providers are able to achieve a high density on their expensive hardware. Serverless is not just a new and emerging cloud execution model. It has also quite unique workload characteristics. First of all, the functions are quite short, often just a few milliseconds or less. Secondly, they have a small memory footprint. And finally, their invocation pattern is quite infrequent, ranging in seconds to minutes. And what that implies is that a multi-tenancy, thousands of functions reside on the same server instance. And to understand this, I want to set this in perspective with what we conventionally have with virtual machines that constantly run on one of the cloud server. For serverless, we have now a lot of tiny functions, and their execution got interleaved on the cores. And what that implies is that while a function is waiting for its next invocations, hundreds or even thousands of other functions will run in between. The question is, what are the implications for on the microarchitecture, which was designed for these conventional workloads? And to answer this question, we studied the effect of interleaving by loading a server with a bunch of functions. Then we increase the inter-arrival time, so the time between two invocations. And by increasing the inter-arrival time, we increase the degree of interleaving, and on the graph it's clear, the higher also the CPI. But if we now consider the typical inter-arrival time for these serverless functions, then we can see there's a drastic increase of CPI for these typical inter-arrival times. But that is quite bad because it means the CPU is wasting a lot of cycles while executing these functions. And to understand now why where the slowdown come from, we did an extensive characterization of the problem by comparing the back-to-back execution with the interleaved execution of one particular function. And what I mean with that is that for the back-to-back execution, we run only this function in isolation. And for the interleaved execution between two invocations, we run a stressor that models the same effect of interleaving as these co-located functions. For analysis, we use the top-down methodology, and we run these experiments on an Intel Broadwell CPU, and from this machine, we collect the CPU performance counters. And the workloads we study were 20 functions that implement a variety in functionality and runtime. We had functions in Go, Python, and Node.js that are not just most commonly used in the cloud, but also representatives for a compiled, jittered, and interpreted language. And all the source code is available from these functions. So if you want to use them by your own, please go to our GitHub page. And what we found, we show in this graph, where you can see the cycles per instructions for the back-to-back execution in the stripe bars and the interleaved execution in the solid bars. We only show a subset of the function as well as the mean overall. And what the graphs show is that the average CPI, that the interleaving increases the CPI on average by 70%. And the reason for that we call lukewarm execution, because we know the function is in memory, but there is no microarchitectural state on chip. And to find out now, or to understand now where these additional stall cycles come from, we use the top-down analysis, which splits execution cycles into different categories. The first category are the cycles where the CPU is retiring instructions. Retiring is good. And if possible, we want all our cycles to be in this category. However, in reality, we have bottlenecks that hurt the performance of the CPU. And in those bottlenecks manifest as stall cycles that manifests as cycles where the pipeline gets stalled. And top-down splits the stall cycles on the highest level into 3 main categories. The first category is front-end bound. That is when the front end cannot deliver more instructions to the pipeline. The second category is bad speculation. That's when we execute on a wrong path. And the last category is back-end bound. That is when the back-end cannot consume more instructions from the pipeline. And what the graph shows us was that the front-end stalls is the largest source of stall cycles. Moreover, 56% of the additional stall cycles come from the fetch latency. So what we found with this graph was that the CPU has really a problem to deliver instructions to the pipeline for these serverless functions. And to understand why the CPU cannot deliver these instructions, we looked into the cache hierarchy. And what we show here in the graph is the mispredictions per kilo instructions for the L2 cache. For the back-to-back execution. The green part shows misses for instruction accesses, and the blue part shows misses for the data accesses. And what we see in the graph is that serverless functions have a very high MPKI of 15 mispredictions per kilo instructions on average. Secondly, these misses are dominated by instruction misses. If we now add also the bars for the back-to-back execution, we can see that in both cases, the MPKI is high and quite similar. Therefore, we shifted our attention to the L3 because the L2 is not the source of the additional stall cycles. And what we can see in the L3 is that, or what you cannot see is that there are almost no instruction misses for the back-to-back execution, just a few for data. But if we now add also the bars for the interleaved execution, we have again back this very high MPKI of 18 mispredictions per kilo instructions on average. And remember that each miss in the L3, for each miss in the L3, we need to read the instructions from main memory, which induces a lot of stall cycles. So the L3 instruction misses really hurt the performance under interleaving. To understand now why we have these instruction misses, we studied instruction traces from 25 consecutive invocations of each functions. And for this, we compared the instruction footprint as well as the commonality at the crash block granularity. And we found 2 key insights. First, there's a high commonality across invocations. And secondly, the functions have a large instruction footprint in contrast to the L2 cache size. And we could take away 2 things from that. First, we have a problem because this large instruction footprint combined with the fact that there are hundreds or even thousands of them, it's clear that all those instruction footprint cannot be maintained on chip under this heavy interleaving. However, with this high commonality, there's maybe a chance to address the problem. And that was exactly our idea, to exploit this high commonality. And our mechanism we had in mind was to, once a function is scheduled, it will accumulate a working set in the cache hierarchy. We want to record this working set, keep it aside while other functions are running. And now when the function is scheduled again, we want to restore this working set so that when the function is executed again, it will experience the same working set as it had seen before. And the implementation of this idea is Choukse. It's a record and replay instruction prefetcher designed for lukewarm serverless functions. And how Choukse works is it records L2 instruction misses in a spatial temporal encoding and stores the records in main memory. And now, once the function is scheduled again, it will use these records to issue prefetches and restore the working set back into L2. Choukse is fully decoupled from the core. It's triggered by a function invocation, and that gives Choukse the ability to run far ahead of the core. And secondly, Choukse operates on virtual addresses, which has the benefit of not being affected by page reallocation, and it's pre-fetching pre-populated TTLB. So in one sentence, Choukse records and replays L2 instruction working sets. To evaluate now this simple idea, we use the Gem5 simulator. We set up a detailed server node. We also set up a secondary node for driving the invocations. We connected these two nodes, and then we run the function on the detailed node and the client on the driving node. And with this setup, we are now able to do a cycle accurate simulation of the full system. We run the same exact software stack with the same container image, the full gRPC stack. And to our knowledge, this is the first support of containers in Gem5. And if you are interested in running containers in Gem5, we made the setups available. So please refer to our GitHub page for that, or come to us. And with this infrastructure, we were now able to do a detailed evaluation of Jukebox. And what I want to present here is our main results, the performance improvement, and the bars here in the graph show the speed up Jukebox achieves over the interleaved execution. And what we found was that Jukebox's simple idea of recording and replaying instruction working set speeds up interleaved execution by about 18% on average. And it does that by covering 85% of the L3 instruction misses, by only using 32 kilobyte of metadata. And with that, I want to summarize. So Jukebox is a simple idea, but also very effective. And with that, I want to summarize our work. So what we first presented is that serverless functions present a new challenge for modern CPUs. We identified a new phenomena of lukewarm execution, where a function is in memory, but there is no microarchitectural state on chip. And secondly, our characterization revealed that there is a severe front-end problem for this lukewarm execution. And finally, we presented Jukebox. It's a record and replay instruction prefetcher that addresses this problem of lukewarm execution. It's a simple and effective solution for cold on-chip instruction state, and it improves the performance by 80% with only using 32 kilobyte of metadata. And with that, I want to say thank you, and I am happy to answer any questions.
The first one is what happens when you have a context switch. And the second one is what happens with data intensive applications. And the third one is, are these improvements, do they include the overheads of serverless platform or only execution?
Can I answer one question?
Yeah.
So the first question was about context switching.
Yeah.
So the thing is that Jukebox is triggered by the scheduler. So that is basically, so when you context switch, you also change Jukebox.
Okay.
So yeah. Second question.
Then how does it happen with data intensive applications?
Sorry, I didn't understand.
How does it happen? How does it help with data intensive applications?
Jukebox addresses the problem of instruction. So if they are data intensive, then of course you also have the data side. So it helps for instructions, but not obviously not for the data.
Yeah, and the third one is those improvements that you showed, do they include the like the time spent on the front end of the serverless platform, everything else, or just like the execution of the function itself?
Just the execution of the function itself.
Okay, thanks.
Hi, I'm Akash from Penn State. I'm a PhD student there. So I wanted to ask, like, serverless functions are essentially used in a public cloud setup where multiple tenants would be running multiple servers on the same metal machine. So were you able to test when multiple workloads, because, any serverless function can execute on any machine. So multiple serverless workloads from multiple users would be executing on the same metal, which means that you're going to have a lot of flushes. And would you get the same speed ups if that happens?
So for this work, we focused on this effect of just the one functions. So we just focus on this one function. We did not look that much onto the effect of others, but that is ongoing work. And
Yeah, so
we
you-
have a
because-
lot of things in mind.
on a public cloud setup, multiple functions would be executing at the same. That is the whole business model of public cloud providers, that they can fix the holes of compute holes with these serverless functions.
Sorry, I didn't.
So they have these holes where the compute resources are idle, and they can allocate these compute resources to multiple users wherever in the data center wherever they can. And that's why you will have multiple users executing on various different resource availability on the data center. And that's why you will have many different sort of workloads running on the same metal machine. So that's something very important to look at, in my opinion.
Yeah,
Yeah.
But it was not a question, right?
Yeah.
So,
Heiner, Litz, UC Cruz. Nice talk. How long does it take to replay one of these instruction footprints? And does the order matter? So do you basically know where the entry point is, and do you try to replay in order so that you can immediately start, or do you have to basically wait until the whole footprint has been replayed?
What we do, it's really a simple design. So we record, and we have this metadata, which has a size of 16 kilobyte for record and also replay. And it so when it starts to replay, it just dumps this into the L2, and there is no
That takes a while depending on the size of the footprint,
exactly,
right?
but that is it's because it's at the beginning it starts at the same time with the CPU, but it overtakes him, and then it continues until it's the end.
Hi, I'm Kaifeng from Princeton University. So my question is, how do you choose the functions for your test? And because your results surprised me that we have a very high L2 cache misses from the instructions, I think. Is that right?
We took different functions from different test benches, and in this study we focus on more shorter functions. And they show this high MPKI for the L2 cache. That's it.
Because for my insights is that like a shorter function should have a very smaller code footprint, so it should not have a large.
The reason for that are these large software stacks in these serverless applications, so that you have a lot of libraries, and it goes all through these libraries, and it touches just a few bytes in each of the cache lines. So, and then you have this large instruction footprint.
Okay, thank you.
Thanks for the question.
Hi, great talk. Dimitrios Lados from CMU. One question, do you have a sense of how much of a benefit you would get if you had something like a stream prefetcher for the instructions that would start fetching? Since the functions are small, like you could just start fetching the instructions from the L2 perhaps without the replay. Like, do you have a sense of if that would work?
You mean just a stream prefetch? So what do you mean by stream prefetch? So that it's also that it's somehow you also stream the addresses because you record them, and stride.
You can do either stride or stream prefetching. It depends on how, because you can organize the code. If it's small, like you could reorganize the code such that you can just fetch it in without the replay, without the record part.
But a stride prefetcher has n plus 1, 2, 3. So, and that is not because it jumps all the way through the code.
Okay, so the code's like sufficient big enough to have that behavior. Okay.
You will not benefit from stride prefetching.
Okay, thanks.
Okay. Was that everything? Okay, thanks. Thanks.
I'm the speaker again. The next talk we have is dynamic global adaptive routing in high-radix networks. The speaker here is Hans Hassan from Past, who is a PhD student working on high-radix networks with Dr. John Kim.
Yep. Hi, good morning, everyone. My name is Hans Kazan, and today I would like to present our work on dynamic global adaptive routing in High-Radix networks. This work is done together with Kwangsun Kim, Yung Yi, and my advisor John Kim at KAIS. So High-Radix networks are widely available in large-scale systems nowadays. So starting from the low-level switch microarchitecture, we have the 64-port EARC and Rosetta switch, which are then used to build interconnection network systems. And these interconnection network systems are then used to connect multiple computers together and build large-scale supercomputers. So High-Radix network is a network with high path diversity and low network diameter. So one example shown here is the flattened butterfly network, and this is for one dimension, and we can basically extend it to multiple dimensions. As shown here is the 2 dimensions. So as you can see, the routers along the dimensions, the X and Y dimensions, are fully connected. And another example is a dragonfly topology, where the routers are grouped into multiple groups, which are then connected with each other. And then there are also a lot of pair works on High-Radix topologies. So with these high diversities, we need to be able to load balance across all the channels. And in order to do so, we need a good adaptive routing algorithm. So the adaptive here means that we are able to adaptively decide whether to route minimally or non-minimally. So let's say we have a packet to be sent from the source to the destination. One option that we can take is to take the minimal path or the shortest path right to the destination. And another option is to take a longer path through the intermediate node, which is what we call as the non-minimal path. And again, the goal is to load balance across all the channels in the network and leverage the path diversity. So one analogy of adaptive routing is with real-world traffic. So let's say we want to go to the Manhattan Bridge from this hotel. And if we go at 3 a.m. where the traffic is relatively low, we can just easily take the shortest path. However, when the traffic is heavy, the shortest path may not always be the best path. So what we can do is we can take a longer path and we can reach our destination faster. So one of the first work in adaptive routing is called the Universal Global Adaptive Load Balancing. And the idea is very simple. Just take the path with the shortest queue. So what it does is it calculates the number of hops times the number of queuing packets queue. So for the minimal path, because it only needs to jump once to the destination node, the number of hop is 1 times QM. And then for the non-minimal path, because we need to jump twice, so 2 times QNM. And we just take the path with a smaller value. So that is for the background portion of this talk. Now I would like to proceed with the motivation for this work. So in general, prior works have trade-offs. They either work on only symmetric or asymmetric traffic, which I will present later in the next slides. And they may also not work for all high-radix network topologies, or the performance may degrade as the channel gets longer, and they does not perform optimally for all traffic loads. So what is asymmetric traffic? So one example shown here is a uniform random traffic, where all nodes essentially distribute the load across all other nodes in the network. So in this case, because load balance is already achieved by the traffic, we only need to route all the packets minimally. And another extreme is what we call as the adversarial traffic, where all nodes that reside in the same router sends the packets to the same destination router. And as a result, all the minimal paths in the network are heavily congested. And in this case, what we have to do is we have to route all packets non-minimally and distribute the loads across all the network. So both of these traffics are what we call as symmetric traffic, because all nodes essentially contribute to the channel load symmetrically. While it is a good parameter to evaluate routing algorithms, we argue that it is not representative of real practical workload, because practically, all nodes in the network won't contribute to the traffic in the same fashion, especially with the emergence of multi-tenancy, where supercomputers can be shared by multiple users and applications. So one example shown here is the node at the left half side of the network runs an application that is communication intensive, and the node at the right half side runs a compute intensive application. So as the result, the channel at the left half side of the network will be more heavily loaded than the channels at the right half side. Hence, asymmetry is created. And in the evaluation section, I will show that prior works may work on symmetric traffic, but then perform suboptimally for asymmetric traffic. So one common method used by the prior work is to add a static bias or a constant value at the routing equation. So if it's added at the left half side, that means if the value is positive, it skews the routing algorithm towards routing more packets minimally. If it's negative, that means more packets will be routed non-minimally. However, this obviously introduces trade-off because it might help with one traffic, but then decrease the performance for the other extreme. So another prior work proposed to let's first estimate the traffic and then decide whether to use positive or negative bias. However, we argue that this is not enough, and these prior routing algorithms are essentially static adaptive routing because they use the same set of rules and the same set of bias values and use that across all routing decisions. So this plot here shows why the static adaptive routing may not be optimal. So what we try to show here is that for the x-axis is the bias value and the y-axis is the latency. And we want to see how the latency differ as the bias value changes. So as we can see here, the optimal bias value or the bias value that gives the lowest latency possible are different across all three different loads. And in the paper, we further show that the optimal bias value varies across different traffics, network topologies, and channel length. So our conclusion is a dynamic global adaptive routing algorithm that is able to adjust the bias dynamically and approach the optimal bias value is necessary to achieve optimal performance across different network configurations. So now I would like to proceed with the algorithm, our proposed algorithm called the DGB, and then go through the two main portions of the algorithm, which is the gradient descent optimization and decoupling. So this is the overall summary of our routing algorithm. And let's say we want to route a packet. And then what we do is we check if this is the time to update our bias, because we update our bias for each epoch. So if it's not the time to update the bias, we just use the existing old bias. But then if it's the time to update the bias, we have two options, either to explore or to optimize using gradient descent. And using this optimized bias value, we decide whether to route minimally or non-minimally. And for this particular talk, I would like to focus more on the gradient descent optimization part. So I would like to first define what is the average latency, which we use as the performance metric. So as I mentioned before, there are two possible paths, minimal and non-minimal path. And the overall average latency is basically the weighted average of the latency of these two paths. And then what we do next is we plot the average latency for different bias values and see how the average latency differ for different bias values. And our observation is that when the bias value is too large, too many packets are routed minimally. Hence, the minimal path is congested and the average latency will increase. However, when the bias is too small, too many packets are routed non-minimally, and the non-minimal path now is congested. So the average latency will then increase. But what we found is that there's a sweet point called the optimal bias, shown as the B star here, where load balance is achieved across the minimal and the nominal path. And at this point is where the average latency is the lowest. So what the dynamic routing algorithm tries to do is, it tries to approach this B star value and use this optimal bias for routing. And to achieve that, we utilize gradient descent. So we update our bias with the difference in terms of latency between the minimal and the non-minimal path. And the goal is simply to reduce the difference in terms of load between the minimal and the non-minimal path. So that is for the gradient descent part of the algorithm. And now I would like to proceed with the decoupling part. So as I mentioned before, we use gradient descent for bias optimization. But then the next question is, how do we find the path latency? Because this is a non-trivial information to be obtained. So most of the prior work tries to use only local information. So let's say we have a packet to be sent from the source to the destination. And what it does is it estimates the path latency as the number of hops times Q, or the number of packets queuing at the next hop router. And this is what we call as local information, because this information is readily available to the source node. However, while it is readily available, it gives only a rough estimation of the overall path latency. So another option that we have is to use global information. So same example, we have a packet to be sent from the source to the destination. And then what the destination node now will do is it will measure the end-to-end latency and then piggyback that information on a packet and then send it back to the source node. However, obviously, the overall process takes time, which is what we call as the feedback round-trip latency. So while global information is more accurate than local information, it can be stale. So to mitigate the trade-offs between local and global information, what we propose is to use decoupled latency. So this is the path latency that we want to estimate. So what we do is we estimate the first hop latency with local information. And then for the latency of the remaining path, we will still use global information. And as a result, we can obtain an estimate of path latency that is more up-to-date and accurate. So using these both two techniques, what we can get is a dynamic routing algorithm that is able to dynamically adjust the bias. So the x-axis here is the time, and the y is the bias value. And the shaded regions show here, it shows the optimal bias value range for 3 different loads. And as we can see here, DGB is able to approach the optimal bias value and stay within the optimal bias value range. So for the last part of this talk, I would like to show some results and then close the talk with a summary. So we use BookSim, a network cycle accurate simulator, and then we integrated it to SST simulator to run trace workload evaluations. And we run our evaluations across different High-Radix network topologies, pattern butterfly and dragonfly. And in summary, what we observe is that our proposed algorithm is able to run well across symmetric and asymmetric traffics. And similar trend is also observed for various High-Radix topologies and for trace-based workloads. So this is one of the trace evaluation that we did. And what I would like to show here is the x-axis shows the performance in terms of runtime for trace traffic. And then for the y-axis, it's with the trace traffic, but we mix it with sympathetic traffic to show asymmetric. So as shown here, UGAL, which is one of the first work, performs very well for mixed trace, but then it performs suboptimally for trace traffic. But then there's a prior work called UGAL PH, which tries to improve the performance of UGAL. While it improves the performance for trace traffic, it introduces trade-off for mixed trace traffic. However, our proposed algorithm, shown as the red star here, is able to achieve optimal performance across symmetric and asymmetric traffic. So we have more details on our algorithms and more comparison with prior works. So please refer to our paper for more details. And in summary, adaptive routing is critical for High-Radix network topologies, but then prior works have trade-offs. So we propose a dynamic routing algorithm called DGB, which utilizes gradient descent to dynamically adjust the bias. And it uses decoupled latency information to obtain a more up-to-date estimation of the path latency and use that to optimize the bias. Thank you.
Hi, I'm Edward from Duke University. So I realized that when you're trying to gather the global information, you're actually adding more traffic to the network. So have you seen that this impacting overall congestion, or are you using like dedicated separate channels for this kind of information?
I see. So we are actually not adding traffic. So what we did is when we piggyback the latency information back to the source, we'll wait until there is a packet to be sent to the source. So we are not creating new packets just to send the latency information back to the source. Yep.
Thank you.
Yeah, thank you.
Given the fact that our session is running late, we'll move on to the next talk. Let's thank the speaker again. So the next talk is ACT, Designing Sustainable Computer Systems with an Architectural Carbon Modeling Tool. And the speaker here with us is Udit Gupta. Udit is a PhD student at Harvard and a visiting research scientist at Meta AI. His research interests are at the intersection of computer architecture, systems for ML, and sustainable computing. And he's starting as an assistant professor in EC at Cornell Tech, summer 2023.
No. How's that? Okay, cool. Well, thanks everybody for being here right before lunch, and I realize we're running a little bit late, so I'll just get right into it. My name is Udit, and today I'm going to be presenting our work on ACT, which is an architectural carbon modeling tool in order to enable the design of sustainable systems in the future. Now, when we aggregate the overall environmental impact of computing across mobile systems, communication infrastructures, and data centers, what we find is that computing accounts for about 900 million metric tons of CO2 emissions every single year. Now, that's on par with the entire aviation industry's footprint, and is about 2 to 4% of worldwide emissions. Not only is that already a huge amount of environmental impact, but on top of that, we can expect computing environmental footprint to grow over the next decade, even double in that period of time. And this is really driven by the growing demand of computing. And so it's really important for us as a community to start thinking about what it means for computer systems to be sustainable themselves. Now, as computer architects, when we think about environmental impacts of computing, we typically think about all of the power and energy consumption that's going into driving our systems or operating them. And while significant improvements have been made on power and energy efficient architectures, it's really important that we start to consider a broader set of environmental impacts across the lifetime of our systems. This includes all 4 phases of life cycles of systems, including how they're designed and manufactured, how they're transported to end users, how we're using these systems over the course of their entire lifetimes, and how we're processing them and tearing them down or recycling these components as well. In particular, we have to start to think about how do we balance emissions across hardware manufacturing and design, or what we call embodied carbon footprints, as well as how we're using these systems across their entire lifetimes, or what we call the operational carbon footprints. Our recent paper, Chasing Carbon at HPCI 2021, showed us that across mobile devices and data centers, hardware manufacturing is actually starting to dominate the lifecycle impacts of hardware platforms. Here we're looking at a breakdown of Apple's environmental footprint in 2019. And what we find is that hardware manufacturing is accounting for nearly 3/4 of their entire carbon footprint. And in fact, hardware manufacturing for integrated circuits like application processors, SoCs, memories, and storage units is accounting for 1/3 of their end-to-end environmental footprints. So moving forward, a key challenge that we're left with is how can we as computer architects start to think about sustainable design by considering the footprint across these end-to-end lifetimes. And while our community has a lot of methodologies and processes to be able to understand and quantify the performance, power, and energy implications of our hardware systems, the same can't be said for carbon footprint and the environmental impacts of our systems. So to address this challenge or to address this gap, today we're going to be presenting ACT, which is this architectural carbon modeling tool. And in the talk, I'll give an overview of what ACT is, how it was designed, how ACT compares to other methodologies available in the community, and how we can start to use ACT in order to enable sustainability-aware design going forward. So first, let's get into what is ACT and what does it look like. So the key part of ACT is this architectural carbon model that we've been designing and developing. So here on the left, what you see is the actual model. And on the right, what you're going to see are the different hardware and software implications and aspects that are affecting the carbon footprint of our systems. At the highest level, carbon is equal to the sum of the operational carbon footprint, as you're seeing in green, and the embodied carbon footprint that you're seeing in red over here. We amortize the embodied carbon footprint of applications running on hardware platforms based on the lifetime of the hardware system and the runtime of individual applications on those hardware platforms. You can start to see how different performance, power, energy, and lifetime implications are going to start to impact the different operational and embodied characteristics of this carbon model. In order to quantify the operational carbon footprints, it's relatively straightforward. We multiply the carbon intensity of the energy being consumed by the system times the energy being consumed by the software application running on a given hardware platform. The embodied carbon footprint, however, the way that we're modeling that is the sum of the packaging overheads and the individual embodied carbon footprint for specific integrated circuits, such as SoCs, memories, and storage units. And this is where the overheads of hardware manufacturing and the scale of our systems is really going to impact the manufacturing carbon footprint or the embodied carbon footprint of our systems. So next, what I want to do is just to start to get a little bit deeper into what some of the backend for this model actually looks like and take an example system. In particular, let's take a look at application processors or SoCs. So to estimate the embodied carbon footprint of SoCs, we multiply the die area of the chip that we're going to be manufacturing times the energy times the impact of the energy, chemicals, and materials used by the semiconductor fab during the manufacturing process. And we also factor in the yield of manufacturing these systems. You can start to see how different aspects of design and manufacturing are going to start to impact this model. So for instance, the area is going to be impacted by the design processes of our systems. The carbon intensity of the fab is going to be impacted by where the fab is located, the carbon intensity of the energy grid and the power grids, and the fab energy, chemicals, and materials, and the yield characterization is all going to be based on the different devices that we're going to be using in our systems and the fabs that we're going to be using to be building and implementing our systems as well. So this is an overview of the SoC. We can actually start to simplify this model a little bit and start to collapse it into an area times the carbon intensity per unit area in order to estimate the embodied carbon footprints of these processors. When we start to do that, we see something really interesting. So here on the x-axis, we have the process technology of the systems that we're developing from 28 nanometer technology all the way down to 3 nanometer technology. And on the y-axis, we see the carbon footprint of these systems as measured by the kilograms of CO2 per unit area. The shaded region is based on the different characteristics of the fabs that are going to be used to be implementing these processors. So the top of the shaded region is a fab that has no renewable energy being driven into it. So it's going to be 100% powered by coal energy. The bottom of it is going to be, the bottom of the shaded region is coming from a fab that might be powered by 100% renewable energy or solar powered. So you can start to see how the availability of renewable energy or different yield characteristics might start to impact these carbon footprints for processors. The solid line is in the middle is what we're estimating for modern fabs like TSMC to be achieving in the not so distant future in about 2025, based on their goal to be about 25% renewable energy driven in that year. So this hopefully gives you an overview of what the embodied carbon footprint model looks like for application processors. In our paper, you can find additional details on how we're adopting a similar process for memory and storage units and all the various different architectural parameters that are going into estimating some of these emissions. But what I want to get into next is actually sharing how ACT compares against other methodologies available in the community right now. So we can actually compare ACT and the model that we've been developing to different product environmental reports available in the community. So here we have two different examples, both coming from Apple. The first is an iPhone on the left, and the second is an iPad on the right. And what we find is that the embodied carbon footprint for the integrated circuit manufacturing is going to be about 23 kilograms for the iPhone and 28 kilograms for the iPad. We can also use ACT to start to estimate the carbon footprint of these components. And when we do that, we see that we can get within about 30% of both of the systems, which is really good for a first order approximation of some of these systems and what we know and don't know necessarily about some of these at-scale products as well. However, the key fundamental difference between ACT and some of these other methods is that for readily available LCAs and product environmental reports, you get a really opaque estimation for where the carbon footprint is coming from. All we know is that the entire system has a manufacturing carbon footprint and what that looks like. But with ACT, you can actually start to get much more finer grained into what are the individual contributions from different application processors, memory units, storage units, packaging overheads, camera ICs, and so much more. And this is really important as a computer architect going forward in terms of how are we designing our processors, what are the different trade-offs and design spaces that we need to start to explore. Okay, so the final portion of this talk that I want to share is how we can start using ACT as a community to enable sustainability aware systems in the future. Now you might be thinking, okay, when I'm thinking about sustainability, this is a really, really wide design space. And that's true. And the way that I like to make sense of it is going back to the tenets of environmental design, which are around how can we reduce our footprints by designing leaner systems? How can we reuse hardware components as much as possible? And how do we recycle discarded components so that we're manufacturing fewer systems over a longer period of time? So in this talk, just in the interest of time, I'm going to go over only two of these environmental tenets through case studies that we conducted. So the first one that I want to talk about is reusing. So reuse is really interesting because I think it's fundamentally ingrained in computer architecture and system design right now. In particular, this trade-off between general purpose and specialized architectures really starts to think about how are we reusing the hardware platforms that we're designing right now. So as a case study, what we do is we're looking at mobile AI inferences running on a general purpose mobile CPU and the more specialized mobile GPUs and DSP units. We put it through the ACT model, and we're looking at the carbon per inference breakdowns for running these mobile net inferences on these different hardware systems. So here we have two different use cases. The first is when we don't have a lot of renewable energy driving or charging our mobile phones on the left side. The second on the right side is when we have a lot of renewable energy available that's going to be charging our mobile phones. On the x-axis also, you see the CPU, GPU, and DSP cases. So we're getting successively more specialized as we go to the right. And on the y-axis, you see the carbon per inference. So as a base case here, running MobileNet on the mobile CPUs, what we find is that the majority of the carbon footprint is actually being consumed by the operational emissions or all the energy being used to drive these systems. And so one thing that you might look towards is actually starting to specialize the hardware platform that you're running these on in order to reduce the impact of all of that energy consumption. What happens when we do this? If we go towards more and more specialized architectures like DSP units, we can actually start to reduce the carbon per inference by a significant portion. And what this means is that these specialized accelerators are actually an optimal design point in this use case. However, we also have another case where we have a lot of renewable energy available to us while we're charging our phones. So this could be the case, like if you go back home and you have a solar panel on your roof, this might be your case. Or if you're part of an energy grid that has a lot of renewable energy available to you, this is what you might be seeing. And in that case, what we find is that the impact of all the energy driving our phones is actually a lot smaller because this energy being consumed is a lot greener. And so in that case, what you might find is that you don't want to pay the additional overhead of manufacturing co-processors like mobile GPUs or DSP units, and a general purpose architecture like the CPU is going to be carbon optimal. In fact, in this case, what we're finding is that by going to the more general purpose architecture, you can reduce your carbon footprint by a factor of 3x. So hopefully this starts to give you a flavor of the wide breadth of design spaces that you can start to think about in terms of sustainability aware system design. The second case study that I want to briefly talk about today is reducing our footprint by designing leaner systems. So going back to this case study around running mobile AI inferences on our mobile systems, we're obviously going to want to continue developing specialized accelerators because of all the performance, power, and energy benefits that they provide. So the question that we're left with is, how can these accelerators or co-processors be more environmentally friendly going forward? So as an example, we're going to look at a specific ASIC, in this case, the NVIDIA Deep Learning Accelerator, or NVDLA, and look at the performance, energy, and carbon trade-offs of the various design points for this accelerator. So in the x-axis here, we have performance, where on the right, you have higher frames per second, so it's better. And on the y-axis, you have the embodied carbon footprint, and the vertical line that you're seeing is 30 frames per second, or a performance target that we're trying to achieve for a streaming mobile application. The black line here, we're actually varying the amount of parallelism that's available in this hardware platform. So as you get more and more parallelism, you're going to get higher performance, but the embodied carbon footprint is also going to be increasing because you have a larger hardware unit that you're also designing and manufacturing. These 2 points that we've highlighted are the performance optimal and the energy optimal design points for this accelerator. However, if you think about the carbon optimal design point, it's going to be this one in green, where you take the performance target and you want to design the system that can meet that performance target, but not be over provisioned beyond that point. And if we design this carbon optimal system, we can actually reduce our emissions by a factor of 3x compared to the performance optimal design point. Okay, so another way that we can think about hardware design is from a resource constraint perspective. So here we're going to impose a resource constraint of area on the x-axis. And on the y-axis, we have the embodied carbon footprint. And the black line that you're seeing is the same design space that we were looking at before. And the green point is the same carbon optimal design that we were talking about earlier. And the vertical line is a 2 millimeter square resource constraint that we have in terms of area. And so, so here the black line has been using a 28 nanometer technology. Another thing that we can do is we can start to design these accelerators in a newer technology node. So let's look at what happens when we go to 16 nanometer. And what we find is that because of the area reduction, we can actually start to reduce the embodied carbon footprint by a significant portion with this newer technology node. However, in practice, this isn't how we interact with hardware design and design systems for the future. If we reduce the area being used by this processor, we're going to use up those freed up resources to design a larger accelerator. And when we do that, we actually end up increasing the embodied carbon footprint of our system by a factor of 30%. And this is a classic example of Jevons paradox, where when you start to improve the efficiency of any application, you're actually going to use up all those freed up resources that you have and deploy a larger system and have higher environmental impacts. Okay, so to recap some of these case studies, what we found in our paper is that by doing this carbon-aware hardware design space exploration, reducing, kind of following the principles of reducing our systems, we can eliminate 3 times our carbon footprint. Reusing systems can have an impact of 2x, and recycling systems can also improve our carbon footprints by an additional factor of 2x. To summarize this talk, what we shared today was how we've developed this architectural carbon model for enabling architects to be able to consider carbon as a first order design metric alongside performance, power, energy, and area, and even cost in our early design space exploration. We conducted various case studies to demonstrate how this tool can be used in order to eliminate carbon emissions for future systems. There's a lot more details available in the paper, in addition to all the modeling parameters, all the industry sources where this data is coming from, the carbon metrics being used to drive this design space exploration, detailed comparison to publicly available lifecycle analyses in the community, more results around the reuse case study, and thinking about the role of reconfigurable architectures or FPGAs and the impact that they can have on the carbon footprint of our systems, and finally thinking about how do we recycle systems for enabling second life and the impact on reliability and performance and energy as well. And finally, I'll just conclude this talk with saying that we've open sourced Axe. So if you're really interested in this work, I definitely encourage you to go onto GitHub, download this code base. And we really hope that this will be a moment where the computer architecture community can start to think about carbon as a first order design metric in our hardware design space explorations. And with that, I'll conclude this talk and take any questions.
Hi, really nice talk and really impactful work. I really appreciate that. I'm Tanvir, by the way. I'm Tanvir from University of Michigan. So it's nice that you mentioned about Jiménez paradox here. So I was just wondering, like, one assumption that Jiménez paradox makes is that the technology stays the same. If the technology stays the same, if you improve the efficiency, then people will continue to use more and more resources, and only then the demand will go up. However, when you are actually improving the efficiency, it can actually have that you can use some other technology. For example, for the data centers use case, when you have reduced the power efficiency, earlier you could not have maybe used renewable sources, but now that you have reduced the power demand, maybe that demand can be met using renewable sources as well. That does not affect the Jiménez paradox. That would not be as hampered as you're describing here. So that should not bother us in terms of efficiency. So what would be your solution so that we can improve the efficiency of real world systems so that we can overcome this kind of Jiménez paradox?
Yeah, that's a really good question. I guess it's about how do we think about efficiency improvements from a carbon perspective and the role of Jevons paradox. So I think there are a lot of cases where we optimize our systems and Jevons paradox doesn't show up, right? Looking at emerging technology, the example that you gave on the data center cases where if we improve power efficiency, perhaps driving our systems with more renewable energy becomes more feasible as well. I think that's great, and the more use cases that we have of that is fantastic. And in my view, I guess that kind of fits into the reduced bucket of the environmental tenants, where you're reducing your footprint as much as possible. The point that I guess I was trying to make was, in a lot of cases, as you improve the efficiency, you're also going to see Jevons paradox show up, and we just need to be cognizant about that and not start to kind of have this this carbon creep in our systems over time. Happy to chat about that more offline as well. Yeah.
Again, great word.
About the scope of the model. Are you in the earlier results you have in the iPhone, the iPad, is that including like the screen, the battery? What's included, what isn't, and what fraction of the overall is your model?
Right. So the question being, what's included in the model? Are batteries or screens and other components included? Yeah, for the end-to-end system. Yeah, so right now we've been taking this bottom-up approach, looking at specific hardware components like processors, memory units, storage units, the packaging overheads and things like that. We don't currently in the model include batteries, screens, PCBs, other, I guess, passive electronics as well, which are definitely going to have an environmental impact as well. And in some cases, depending on the system that you're designing, they could have a very large and dominating impact. That's something that we're hoping to include in future systems. Right now, we're kind of focused on the immediate, I guess, areas where like computer architects can interact with, and then kind of hoping. One of the reasons that we're open sourcing this tool as well is that try to build up more of a community around this space. And if you have more data around battery systems or PCBs or these other system components, I love to work with people on integrating that into a broader set of resources for the community as well.
So from like an Amdahl's law point of view, though, like what fraction of the overall carbon footprint are you covering?
Yeah, so from an Amdahl's law point of view, earlier in the talk, I showed kind of like the pie chart from Apple's perspective. The largest chunk in terms of hardware manufacturing is coming from integrated circuits, which is what we were focused on, and that's one of the motivating reasons of the way that we designed ACT. It's about a third of Apple's entire footprint, and about half of their hardware manufacturing footprint is coming from integrated circuits. PCBs, batteries, and everything else are kind of the other components that I guess from an envelope perspective are a little bit smaller for mobile processors.
Thank you.
Yep.
The session is running really late, and we have another session that's supposed to happen right after school day. Just one more question from Akshitha, and then that's.
This is such wonderful work, Udit. Thank you for your presentation. I'm Akshitha from Carnegie Mellon. So I guess my question is, I'm wondering if I can use this model to make runtime decisions in a data center. So for example, you were talking about the operational costs, but in the data center, a lot of times, especially when you have dark silicon, there are parts of the chip that achieve carbon neutral status even before other parts of the chip. And so can you now make scheduling decisions, pricing model decisions at system runtime using this model? And if so, how would I incorporate that?
Yeah, great question in terms of how does this scale up to data center scale systems? Yes, it can, I would say, to first order. So we do have an impact from the software application that you're running, especially in cloud services where you have more of like an elastic infrastructure model in terms of if you don't use up certain infrastructure resources, those get freed up. And so your embodied carbon footprint from that becomes reduced. More broadly, I think there's a role of capacity planning teams to play here in terms of how they're going to be provisioning systems in the future as well. But I guess the TLDR to your question is, yes, you could use a model like this to make decisions on how you're going to be scheduling workloads across different processors and things like that. One area that we're hoping that we're going to get more data on from industry are server scale lifecycle analyses. Right now, the community has a distinct lack of them. And so the more and more of those instances that we get, the better and more informed decisions that we can make. But hopefully ACT is a starting point for that.
Great work again. Thank you.
That's a lot of great work. Let's start with the speaker.